We're continuing to cover different techniques of integration in Chapter 7. In this video, we're going to talk about how to integrate rational functions by partial fractions. So in this section, we're strictly talking about integrating rational functions. So not just any ratio of expressions of x or expressions of a single variable. We're just talking about rational functions, how to integrate rational functions. And so what is a rational function? Well, we learned in algebra that a rational function is a ratio of polynomials. So if you have p of x divided by q of x, and p of x and q of x are both polynomials. That's a rational function. Now, at the end of this section, we are going to talk about cases where you don't have a rational function. You have a ratio of expressions that aren't polynomials, but via substitution, you could turn that ratio into a rational function, integrate it, and then substitute back. Okay, but in general, though, the technique that we're covering here is strictly for rational functions. And so to do this, to perform the integration, what we're going to do is, so we'll start with an integral like this. If you look here, so here's a rational function. We want to integrate this rational function. And so to perform the integration, what we're going to do is we're going to break down the rational function into a sum or difference of simpler rational functions. And then from there, we can break up the integral into separate integrals and then integrate the simpler rational functions separately. Okay? And the process of breaking down a rational function into a sum or difference of simpler rational functions is we learned this in algebra. It's called partial fraction decomposition. So to integrate a rational function, you know, if it's simple enough to where you can just integrate it as it is, then do that. But if it's too complex of a rational function that you can't just integrate it by normal means, then you perform partial fraction decomposition on it and separate that integral up into simpler integrals. Okay, and so obviously to integrate most rational functions, you need to know how to perform partial fraction decomposition. Now, I'm not going to go into too much depth on the process of partial fraction decomposition in this video. This is something that we go through in full detail, thorough detail in algebra. But if you're following through the playlist, the calculus playlist, then just before this video in the playlist, I added the algebra video where we go into detail on how to perform partial fraction decomposition. So make sure you check out that video. It's in the calculus playlist just before this video, or you can search on YouTube, Aberry Engineering partial fraction decomposition. It's an algebra video. Okay, now, so if you've watched that video, then what you learned is that if you have a rational function, the first step is that you check to see if the order of the numerator is greater than or equal to the order of the denominator, the order of the polynomial. If it is, then the first thing you're going to need to do is do polynomial long division to separate that rational function into an expression that contains a rational function to where the order of the numerator is less than the order of the denominator. So if we look here, here's a case where you start off with the rational function where the order of the numerator is greater than the order of the denominator. So they do polynomial long division first and get this. And so you can integrate this, you can integrate this, you can integrate this, and then you're always going to be left with a polynomial that has the order of the numerator is less than the order of the denominator. And when it comes to partial fraction decomposition, to perform the process, you need to have a rational function that has the order where the order of the numerator is less than the order of the denominator, like this. However, this is already simple enough. There's no partial fraction decomposition to perform here. But in some cases, it might be where you perform polynomial long division and you get a rational function that it is the case that the order of the numerator is less than the order of the denominator, but it's still complicated enough to where you need to perform partial fraction decomposition. All right, and that's what they're showing here in general. If so, the order of p is greater than the order of q, greater than or equal to, you perform polynomial long division. You get some function of x, which that would be equivalent to this, plus an r of x over q of x, to where the order of r is less than the order of q. And this is what, depending on how complicated it is, we may need to perform partial fraction decomposition to integrate it. If it's simple enough, we don't have to do that. But if we can't integrate it just by normal means, we're going to have to perform the partial fraction decomposition. Okay, so if we come here first, we see that they did the polynomial long division, and we know how to integrate this, this, and this. And then integrating this here, you can see that if you kind of take the 2 out front and you're left with 1 over x minus 1, then if you think about the natural log of the absolute value of x minus 1, that would be the integral, right? The natural log, because the integral of 1 over x is natural log of the absolute value of x. So if you're integrating, in the result of the integral is a natural log, it's going to have the absolute value. So the integral of the absolute value of x minus 1 is 1 over x minus 1 times the derivative of x minus 1, which is just 1. So it's 2 times the natural log of x, of the absolute value of x minus 1. So you see, you can integrate these simple, it's not a problem to integrate once you have a simple enough of a rational expression. You know, this 2 is a polynomial, right? X minus 1 is a polynomial. If you have a rational expression that's simple enough, you can just integrate it with normal means. Okay, so we have this r of x over q of x, where the order of the numerator is less than the order of the denominator. And so what we know is that we're going to be able to factor, we can factor any polynomial, no matter what it is, into a product of linear factors and quadratic factors. And that's it. No matter what the polynomial is, it can be factored into strictly a product of linear and quadratic factors. It can be all linear or all quadratic or a mixture of both. And so once we have that denominator factored, then we're going to write out the form of the decomposition, and that form will always consist of an addition or subtraction of some specific types of rational functions. So it's going to be every single time you perform partial fraction decomposition, no matter what the rational function is, you're going to have some mix of, it'll be one of these terms, one or more of these terms. So you'll have a linear factor to the first power, so ax plus b to the first power over just a constant. Okay, you might have a linear factor to some power other than 1, and it'll be just a constant in the numerator. You could have a quadratic factor to the power 1, so it would be, you know, and these the ax and the b, the a and the b here don't have to be the same thing. I mean, let me, just to be clear, right? So you would have, you know, cx plus d to any power n, let me do n1, you know, these are all different. Okay, now you could have a quadratic factor to the first power. So, okay, we've got ex squared plus fx plus g to the first power, and then you would have cx plus d. And so then maybe d is 0 and c is a number. Maybe c is a number and d is, or c is 0 and d is a number, you know. But it would be just something like this. Or you would have a quadratic factor that's raised to some integer power. So that would be hx squared plus ix plus j to the n2 power raised to ex plus f. Okay, this is it. Every partial fraction decomposition is going to contain like, you could actually, in general, it's going to be something, only terms that look like this. Every single term in a partial fraction decomposition is going to be of one of these four forms. A rational function with a linear factor in the denominator to the first power and a constant in the numerator. A rational function with a linear factor in the denominator raised to some power other than 1, like 2, some positive integer other than 1, like 2, 3, 4, etc., with a constant in the numerator. A quadratic factor raised to the first power with a cx plus d in the numerator, where c could be 0 and d could be a number, or vice versa. Or a quadratic factor with a positive integer other than 1 power, with a constant times x plus another constant in the numerator. Okay, now you might be saying to yourself, well, wait a minute. I'm familiar with factoring. I studied how to factor in algebra, and there's definitely cases where you've got a polynomial that's greater than order 2 that can't be factored any further. For example, like x to the 4th plus 1. You can't factor that any further, and that's not a quadratic. That's not a linear factor. Well, okay, the whole idea that any polynomial, no matter what it is, can ultimately be broken down into strictly products of quadratic and linear factors, that comes from the fundamental theorem of algebra. And so how you would actually factor something like x to the 4th plus 1 even further is beyond the scope of what we're going to learn in this video and in this course, and even beyond the scope of what we learn in just the general algebra course, okay? But it's just still something to keep in the back of your mind, something to note that, so the partial fraction decomposition process, all of the rules and the methods are based on having strictly linear and quadratic factors in the denominator. And so just keep in the back of your mind that if you did know the techniques to break down any polynomial, past the techniques that we learned for factoring in just basic algebra, if you knew the techniques to truly break down any polynomial into linear and quadratic factors, then the idea is you could perform the partial fraction decomposition process on any polynomial. So keep that in the back of your mind. But since that's beyond the scope of what we're doing in this course, then the only problems that we're going to work are going to be with rational functions, to where the denominator, we can use the factoring techniques that we learned in algebra, to where we'll be able to break down the denominator of any polynomial that we're working with into linear and quadratic factors. And so it's those types of rational functions that we're specifically talking about in this section. Okay, now, however, if you did have a polynomial where you got a factor such as x to the 4th plus 1 in the denominator, what we're going to talk about in the next video, we're going to go over how you can use substitutions to convert those types of polynomials into polynomials that you can factor the denominator to linear and quadratic factors, and then apply the methods of this that we're learning in this section. Okay, and so again, in this video, we're not going to get into the details of performing partial fraction decomposition. I'm going to assume that if you want to work example problems on doing this, you could go check out the algebra playlist. But we're also going to, when we work example problems in this section for integrating, we'll perform those videos. We're going to do the full partial fraction decomposition for each problem. But as far as going through this section, we're not going to talk about how to perform the process. What we're going to talk about is, how do you integrate each one of these types? Okay, so we already talked about the simplest case of for this here, a linear factor raised to the first power and then a constant in the numerator. And so, like, here we had 2 over x minus 1. Now, okay, it's a little more complicated if you have, 2 over, let's say, 3x minus 1. So what would you do there if you had? Well, okay, you would, and then if you think about, so the natural log of the absolute value of 3x minus 1, What is that? What is this derivative? It's 1 over 3x minus 1 times 3. Right? It's 1 over 3x minus 1 times the derivative of 3x minus 1, which is 3. So you put a 1/3 here. But then you have the 2 out front, so this ends up, this integral then ends up being right? So a rational function with a linear factor in the denominator raised to the first power is easy. You actually, I mean, you could do, another way you could do this is you could do a substitution. So you could say u is equal to 3x minus 1, and you get the same result if you don't want to just do it mentally. Okay, and so, it talks about, so here we're going over, all we need to do is learn how to integrate these. These are the 4 cases. Well, they show 2 here. It's a over ax plus b I to the I power, but we just learned about when I is equal to 1, but we also have the case when I is greater than 1, and then here, same idea. I could be equal to 1 over the quadratic, or it could be greater than 1. And so for case 1, they talked about if you had, these were just distinct linear factors, so all of the linear factors, the entire decomposition was strictly linear factors where the raised to the first power. Okay, so this was the decomposition. Here we're trying to integrate this, and here's the decomposition. So they solve for A, B, and C. And this is the result. And so here you can do it mentally, or you can, if it's like a case like this, you can make a u substitution. Say u is equal to 2x minus 1, but again, a linear factor raised to the first power in the denominator, it's you can just, those are simple. Okay, so now case 2, we want to look at how do you integrate a rational function where you have a constant in the numerator and then a linear factor in the denominator raised to a power, a positive integer power other than 1. Okay, so you perform the partial fraction decomposition here, and you get something like this. So we know how to integrate this and this, but what about these? Okay, so here's an example. You're going to integrate this function. They do the decomposition, and so here's the decomposition, but then they solve for A, B, and C. Okay, and so how do you integrate this? Well, okay, this one specifically, we could just do a u substitution. Right? So if we had if we say u is equal to x minus 1, du is equal to dx. Okay, so this is minus 2 over u. Minus 2 over, right? And so in general, that's how you're going to integrate a rational function like this, because you just have a constant in the numerator. There's no x. So all you got to do is just make the u substitution for whatever's in the power in the denominator. Just say u is equal to whatever's in the power, and that will work every time. Right? Even if you had 5 over to the 5th, if you say u is equal to 3x plus 2, du is equal to 3 dx, so you got 1/3 du is equal to dx, so 5 over u to the 5th du, 5/3 times integral of u to the minus 5 is u to the minus 4 over minus 4. So minus 5 over 12 u to the minus 4. Minus 5 over 12. Like that. All right, so now we want to look at if we've got a quadratic factor to the first power. So the first thing they talk about, if we look here, in order to evaluate this, we're going to complete the square for the quadratic factor, right? So we can write it in a form of x squared plus a squared. We might have to complete the square and make a substitution, but given any quadratic, we can put it into a form x squared plus a squared. And so here they give an integral for when the a here is 0. So you just have a constant in the numerator, right? You can bring the constant out and you get dx over x squared plus a squared, and here's the integral. Okay, but now what about the general case? What if you have a ax plus b in the numerator, where a and b are both non-zero? Well, if we come here, they go through this example, and what they show in this example, if we come to the next page, so the general procedure is you're still going to use completing the square to put the denominator into this form, and then from there you're going to separate the integral into two separate integrals. Then this integral you evaluate using the formula we just talked about, and then this integral you can make a u substitution, right? Okay, and so this is it. You'll always be able to make a u substitution here because we're always going to have a quadratic, right? It's going to be a u squared. It's a quadratic that we completed the square with, so it's always going to be a u, or a variable squared, and then a variable to the first power, so you can make the u substitution. So any of the partial fraction components that is a quadratic denominator factor with it to the first power, and then you'll have in general like a cu plus d, you can solve in this way. U substitution here, and then the formula that we just talked about, this formula here for the quadratic factor to the first power. Okay, the last case is if we have a quadratic factor raised to an integer power other than 1. And so to deal with this, we're going to complete the square of the quadratic inside. So like here, we can turn any quadratic to a power other than 1 into a form like this by completing the square, right? Okay, but in the numerator we'll have like a ax plus b, and so we can separate this into two separate integrals. And for the integral where you just have like an x term over this, you could just do a substitution, right? And so the only issue then is something like this. So like if you had ax over, right, make a u substitution. You say u is equal to x squared plus a squared, and then that'll work. But if you just have this, then what do? And so it talks about here that, so you can make the integral to a form like this, like, you can take out the constant, and you'll have 1 over, something like this, x squared plus 1 squared. And it says one way to integrate such a term is to make the substitution x is equal to tangent theta. So they're saying that we could do a trig substitution. So it might not be tangent theta. It depends on if it's x squared minus a squared, x squared plus a squared, depends on what it is. We can do a trig substitution is what they're saying. And it says another method is to use the formula in exercise 72. We can take a look at that, but let's just go ahead and say the default is going to be for something like this, we'll use a trig substitution. Okay, and so that's it. That's all the cases. Once you perform the partial fraction decomposition, then we just went through how to integrate, every one of those separate cases. All right, now it says sometimes partial fractions can be avoided when integrating rational functions. For instance, although the integral could be evaluated using the methods we just discussed, we can see there's a u substitution here. If u is equal to x times x squared plus 3, then u is equal to x cubed plus 3x. Then du is equal to 3x squared plus 3. And so that ends up, if you make this equal to u, and you take and the du is going to be of this form. So just make, they're saying just, take a close look to see if there's not a u substitution or some other method that can work outside of doing the full partial fraction decomposition. Okay. So now this last section is talking about there's cases where you don't start with a rational function, but you can make a substitution to turn it into a rational function and then solve it with the methods we just outlined. So some non-rational functions can be changed into rational functions by means of appropriate substitutions. In particular, when an integrand contains an expression of the form the nth root of g of x, then the substitution u is equal to the nth root of g of x may be effective. Other instances appear in the exercises. So yeah, we'll take a look at these other instances, but they give, so there's certain instances with the integrand where you can make a substitution and it'll turn into a rational function. And here's one instance, and we're going to look at the other instances in the exercises, but they're saying if the integrand contains the nth root of some function, so like this. Well, if you say that, if here you say that u is equal to the square root of x plus 4, then u squared is equal to x plus 4, so x is equal to u squared minus 4, and so now you get dx. Dx is equal to 2u du, and so now you make the substitution, and you get this. And now you can solve it, right? So any integrand where you've got the nth root of some function of x, consider if you've exhausted all options for how to solve it, right? So here I don't think you can't do a trig substitution, you can't do a u substitution. Then like the u substitution that we're for the basic u substitution. But here you can say do another u substitution and turn it into a rational function. Okay. So now let's work some example problems.